We were deep in the big data revolution when the volume, the velocity, and the variety of data completely overwhelmed the systems used to store, manipulate, and analyze that data. Now we're in the midst of an artificial intelligence revolution, but it's important to remember that big data hasn't gone away or become irrelevant. Rather, big data has become the new normal. It's everywhere, and in fact, it's big data that makes artificial intelligence possible. I'm Barton Polson, and in this course, we'll explore the ways that big data has developed in parallel with social media and the Internet of Things. We'll see how it's added unexpected value to enterprise analytics by improving business strategy and customer interactions. We'll introduce some of the common approaches to analyzing big data and evolving methods for implementing its insights. We'll see how big data relates to data science and machine learning and artificial intelligence, and we'll discuss important issues surrounding data governance and privacy. But this is not a technical discussion. I'm not going to demonstrate code or walk through specific algorithms. Rather, this discussion focuses on the concepts that enliven big data. So if you want to know how you can thrive in the world of big data, data science, machine learning, and artificial intelligence, then regardless of your technical background, this course can give you a roadmap and a better understanding of how to draw on data to do the things that are important to you and to do them more effectively and more efficiently. And so with that in mind, let's get started with big data in the age of AI. The one thing we know absolutely for sure about big data is, that it's really big. There's a lot of data. It's big. But, what counts as big data changes with the times. Once upon a time, a bunch of punch cards might have been big data. Or back in 1969, this was a massive amount of programming. This is Margaret Hamilton with the code for the Apollo guidance computer, for which she eventually won the Presidential Medal of Freedom. And then what might be big at one time becomes normal or even small at another. So, for example, back in 1992, I got my first computer, an Apple Macintosh Classic II, with the optional larger 80-megabyte hard drive. I got all the way through grad school. I wrote my PhD thesis on that computer. And now I have a relatively modest MacBook Pro, and when I'm home, it's connected to 10 terabytes of external storage. That's 125,000 times as much storage as my first computer, and truthfully, I bumped up against the limits. So it's massive by comparison to my 1992 self, but it's middling for consumers and really puny by any commercial standards. And so if we want to think about really what do we mean by big data, given this relative shifting frame of reference, well, one thing that's pretty consistent is the definition that relies on what are called the 3 V's of big data. And so the first V, the first characteristic of big data, is volume, simply meaning there's a lot of it. And the second is velocity, having to do with the speed with which the data arrives. And the third one is the variety or the nature and the format of the data. Take those together and you have what most people would consider big data. And I want to talk about each of these a little bit separately. So volume is the most obvious one. This is when you have more data than fits in a computer's RAM, its memory. Or maybe you have more data than fits on a single hard drive and you have to use servers and distributed storage. I mean, think, for example, about the data on Facebook's 2+ billion users. You can't put that on a single computer. Or the information on Amazon's 120+ million items that they sell online. Keeping track of all of that is obviously going to overwhelm any one computer or even a collection of computers. Next is velocity. A gentle breeze through the trees is nice, but a hurricane is a whole other situation. The velocity refers to data that comes in rapidly and changes frequently. So think about, for instance, it's been estimated that nearly 200 million emails are sent each minute of each day, or that 5 billion videos are watched on YouTube every day. If you're trying to keep track of this stuff as it happens, it's going to be a completely overwhelming job. And then the third V is variety. Data comes in a lot of different formats, and you can have video, photos, audio. You can have GPS coordinates with time and location. You can have social network connections between people. And all of these represent distinct kinds of data from the regular rows and columns of numbers and letters that you would expect to find in like a spreadsheet. And all of these require special ways of storing, managing, manipulating, and analyzing the data. Taken together, those usually constitute big data. Another way to think about it is big data is data that is hard to manage. It's the idea like some animals are a little more challenging to deal with and have not been domesticated like the zebra. Big data is a little like the zebra of the data world. It's simply not easy to work with, not through conventional standards, and you're going to have to be very adaptable to get the value out of that data. Now, I do want to say something historical about the term. This is Google Trends data on the search popularity for the term big data on Google. And we have data from 2011 through 2019. And what you can see is there's an obvious peak right there in the middle at October of 2014. That is when the Google searches for big data were the most common overall. Now, this doesn't mean that people don't care about big data anymore. You see how it's gone down maybe a third, maybe even 50% since then. Well, there's a saying that a fish, or in this case a seahorse, would be the last to discover water. That's because it's everywhere around them. It's literally the medium in which they live and move. The same thing is true for big data. When people think about advanced data work these days, the mind is immediately drawn towards artificial intelligence and machine learning, the way that the mind was automatically drawn towards big data a few years ago. But to understand the connection between big data and these other fields, because there is a connection, it's worth reminding ourselves about what they all mean. So for instance, artificial intelligence is a field in data science and in computer science, and it's the field that focuses on techniques that allow computers to do things typically done by humans, like play a game of Go or classify photos or evaluate MRIs. And it's usually done in a way that shows adaptability to new circumstances, or shows intelligence and flexibility in responding to the data that's coming in. Machine learning, on the other hand, is a collection, a rubric of algorithms that can find patterns in data to predict outcomes. Like, for instance, whose face is this, and is it the person that owns the phone? One of the things about machine learning is that most of them improve over time as new data comes in, and especially as there is more labeled data where you know what the particular outcome is, it can improve and develop over time. And machine learning algorithms go from the relatively simple, like linear regression, to the amazingly complex, like a deep learning neural network. And you can also look at the connection between these fields by looking at Google Trends search data over time. So this is showing us the relative popularity of search terms over the last 8 years, from 2011 to 2019. The first one, which we've seen before, is the pattern for big data, which peaked in 2014. And it's gone down a little. It makes you think people don't care about big data as much, perhaps. This green one is the curve for machine learning, and you can see it has skyrocketed over the last couple of years. And this third one is artificial intelligence, and truthfully, I was surprised that it was lower than machine learning. But here's what you need to know about the relationship between artificial intelligence, machine learning, and big data. It works this way. I actually want to go back to the 1600s to Isaac Newton, who said, "If I have seen further, it is by standing on the shoulders of giants." And it turns out that if artificial intelligence and machine learning have thrived over the last few years, and they have, it is because they have stood on the shoulders of big data. So the relationship between these fields is in addition to, that machine learning and artificial intelligence are in addition to big data, not instead of it. They rely on big data. They can't do their work without it. I'll give you a quick idea about this. AI requires massive data. The theory of neural networks has existed since the 50s, but it was only in the last few years that there has finally been enough data to make this work well. And that has to do with the volume, the first V of big data. Second, the data is streaming constantly, especially with social media data and sensor media data. It's coming in tremendously. That's the velocity of big data that makes so much of the machine learning possible. And then finally, AI and machine learning involve novel data like images and movies and audio and so many other things that don't fit into standard relational databases. That's the variety of big data where AI has been The big data revolution has happened because data has grown, but it hasn't happened in a gradual process like a little sprout coming up out of the ground. I mean, that would be an example of what's called linear growth. For each step forward in time, you move the same step upward to get this nice straight line. That's easy to deal with. Rather, data growth has been exponential. Here I take the exact same line, but I put it way down here because here's an exponential curve. This is actually 2 to the power of x. And, you don't even get to see how far it goes over to 10 because at that point, it's got a value of over 1,000, 1,024 to be exact. That's a whole lot more than the 10 we had with linear growth. This is huge. But you know what? The data revolution is growing even faster than this. We can shrink that one down, and we can draw a curve that shows the x to the x. So we take the number on the bottom, the 4, the 5, the 10, and raise that to its own power. When we do that, we get a curve like this. You don't even get to see how far it goes because by the time it gets to 10, it's at 10 billion. This is the kind of growth that we're dealing with in the data world. And my personal impression is that at this exact moment, we're right here at this inflection point where things are taking off. And so when we're talking about data growth, it's less of a carefully nurtured sprout popping up through the ground and more of a barely controlled explosion. Really, it's an exciting time. And there are a couple of major contributors to this explosive growth. The first major candidate for this explosive growth is social media, and the second one is the Internet of Things. Now, there are many others, but these really play a starring role in the extraordinary growth of the big data world. Let's talk about how this works. First off, there is the feedback. We have the Ouroboros, the snake that's feeding on itself. And this is like social media because social media begets more social media. I mean, think about it. A person puts a post online, that post gets liked. Each like is an additional piece of data with a fair amount of metadata that goes with it. Somebody puts an image online, that image gets tagged and it gets shared with anybody who's in it and it gets put into forums that use the same tags. Or somebody has a follower, they put something online, and those followers share that content and multiply the reach of the post. Also, of course, the fact that more and more people are online and more people have social media profiles. And so there's this incredible growth. It's not just that it's doubling, it's the X to the X kind of growth. It just goes absolutely through the roof with social media. Now, another one is the Internet of Things. That's IoT. And the classical examples of Internet of Things include things like smart homes. So I've got a smart thermostat. It knows when we're home. It talks to our phones. It can tell what's going on. And maybe you've got lights and a security system, and maybe you got a smart lock, and maybe you've got all sorts of other systems that are connected with each other. They're communicating constantly. And outside of the home, you can have a smart grid where the city knows about the traffic levels. It knows about how much electricity is going between the generators and the various buildings and houses. It knows what's going on with the water system. There's so much information being exchanged here through sensors and networks that it, again, has the explosive growth. Another one that falls into this category is self-driving cars, which gather an extraordinary amount of data from the sensors they have all around them, and they communicate to each other. And the time will soon come that they communicate directly with the road and with the traffic signals, and there are so many different ways to gather all this data. And it gets even more complicated because the quality of the data has changed over time. Now, by that, I don't mean good data versus bad data. I mean that we start with text. Text comes first. When you send text messages, you started with your little flip phone and you send your little tiny text message, which actually was text. Text can be measured in kilobytes. But soon, for instance, you learn how to do audio and you can send a voice message, or a sensor for your home can give you the audio of what's happening. That's usually measured in megabytes. And then eventually you get to video. Say, for instance, you have a doorbell. It's now giving you HD video over your phone of who's there at the door. Video can be measured in gigabytes. And so we're not only increasing the number of things that provide the data, but we're going up the ladder to kinds or qualities of data that are much, much larger and also might move from the structured to the large and unstructured. I love old books. I love the feel. I love the look. I love the formal typesetting, the page-long paragraphs, the formal language, the complete absence of footnotes and references. But they're musty, they're fragile, and really they're risky to lend out. You don't know if they're going to come back intact. They're hardly how I would want to store my operational data. And so after the era of books as data, we got to go to digital data sets. But so often the data did, and frequently still does, exist as a local file on one person's own computer, where it may not be able to do much good except for that one person's desktop. Organizations have always been trying to find ways to get the message out, and several developments in data storage have helped with that goal and helped deal with the massive quantities of data that are part and parcel of big data. The first solution, the first step in this direction was the creation of data warehouses. A data warehouse is a unified place to keep an organization's data sets. So think of it as a server that has all the data sets on it. Now, there are several advantages to data warehouses. Number one, the data is typically well-structured and curated. And it's well-structured in part because data warehouses often could only take one kind of data, and it would usually be a relational database with the rows and columns of tables. And in addition to that, a data warehouse may contain discrete organizational units. So, for instance, accounting might have their own part of the warehouse, and sales might have their own part of the warehouse. And this was one way to organize things. And these were very popular, say, for instance, back in the 70s and 80s. But there was a problem, and that you ran the risk of ending up with a data dead zone, an abandoned data warehouse. The reliance on structured data worked well for a lot of purposes. But the explosion of big data brought in enormous amounts of unstructured and semi-structured data that didn't fit well in the systems. In addition, warehouses sometimes perpetuated the existence of organizational silos, or these walls between units, that didn't communicate well, and truthfully, that undermined some of the promise of the data revolution. And so, for many organizations, the data warehouse kind of came, it solved some problems, but then it seemed to bring along some potential problems of its own. That led to the development of our next solution and next metaphor, the data lake. This is a data storage that holds data that is structured and semi-structured and unstructured. Any kind of data can go in there. So it's enormously flexible. And it's designed to do away with data silos, that all of the organization's data from every unit can go in there. And so it's potentially available to whoever needs it. And really, it's the existence of data lakes through things like Hadoop that made the big data revolution possible. But just as with data warehouses, there are some potential risks with data lakes, and that is you can end up with a data swamp. If the data lake isn't well maintained, if mistakes in the data aren't fixed, if adequate metadata isn't provided, if multiple but different versions of the same data are coexisting, if formats aren't adapted to the software used, you run the risk of getting this swamp-like situation, which can be a dangerous place to get lost and really becomes a place where data go to die. And so people came to recognize there were some limitations to this approach as well, which leads us to the current preferred solution, which is the cloud. The idea here is that a data cloud is something that contains data, like a data lake, that is structured, semi-structured, and unstructured, so it's very flexible in terms of the contents, but it doesn't rely on a local server. It doesn't rely on local maintenance of the equipment because it's off somewhere else. I mean, this is when you use things like Amazon Web Services, better known as AWS, or Microsoft Azure, or Google Cloud, among others. And also, because it's fully online, it's more accessible, and truthfully, it's more adaptable. You can get more space immediately. You can get more computing resources immediately as you go. And so there's some huge advantages to storing and working with big data in the cloud. But as with every other solution, there are some risks, and I'm going to call it data dissipation. The major risks of storing data in the cloud have to do first with security, where the organization may not be keeping track of who has access to the resources, or it might be susceptible to hacking. And second, there's cost containment. When things are infinitely expandable at any time, you may not be keeping track of the costs that you're racking up. And third, there's the remote possibility that the services you use might become temporarily inaccessible, or they may disappear completely. And so you do run the risk of your data kind of dissipating or not knowing what's happening there. Because we are in the data cloud era, it's worth pointing out a couple of variations that have become particularly popular. One is the multi-cloud, also called Polynimbus. This is using several different cloud storage and computing providers simultaneously. So you might use both Microsoft Azure and Google Cloud, and use some IBM cloud computing resources. And the point here is you actually can integrate them so they're in a single heterogeneous environment. So it's as though they were in a single thing. Now, that's one popular approach because it lets you use the strengths of each of these providers. There's also hybrid cloud. This is where you're using both a public cloud like AWS and you're using a secure private cloud. Think of a local server. And what that lets you do is it lets you keep a lot tighter control on what happens here. And it's possible also to move back and forth. You can take things from the private cloud, push them into the public cloud when you need to expand, or if you need transparency, but times you need extra security, you bring it from the public to the private. And so there are a lot of variations that can be used to meet the demands of your organization's data, computing, and the regulatory environment. And so there are a few things to think about when looking at these different approaches, the data warehouse, the data lake, the data cloud, along with the multi-cloud and the hybrid cloud. Number one is accessibility. Some of these allow more access to more people and from different situations. The cloud's going to be the best at that. The data warehouse is going to be the most limited in that particular respect. There's also the flexibility. What kinds of data can you put into it? And also, can you scale up your resources as needed? And then the third one is security. How much control do you have over your data? How much control do you have over your costs? And how are you able to meet the demands of the regulations that you're working with? Using these three criterions, as well as things like the cost of purchase to maintain and the learning curve to get started on any one of these, your organization can choose. Do you want a data warehouse? Do you want a data lake? Or do you want to work in the cloud? Or maybe there's even a situation where you do want to keep those files on a single computer for the tightest possible control. But any one of these is going to allow you to make an informed choice about how you deal with your data, especially all the variations that constitute big data and the promise that it has for your organization. Sometimes when you're thinking about strategy, you get to choose between going for a single big win or maybe many small wins. For example, in baseball, you can go for the glorious home run, or you can play small ball and just focus on getting runners on base and systematically moving them forward. If you're writing novels, you can hope to have a massive bestseller, which is hard, or you can write a dozen books that sell well within a particular niche. And when it comes to helping people, you can engage in a giant, newsworthy, grand gesture, or you can focus on 1,000 small acts of kindness. You have a similar strategic choice in big data. You can either put all of your data and all of your processing hardware in a single massive server farm or other central location, or you can spread out the work to many, many small processors. In big data, this latter approach goes by a couple of different names. One is edge computing. And the idea with edge computing is that you have central storage and processing in the regular big data model, and that would be shown by this central unit in the middle of this network, and then you have connected devices at the edge of the network. But in edge computing, those devices on the edge, the ones on the periphery, can also store and even process data, taking some of the workload away from the central computer. Another name for this is fog computing, and this comes from the idea that you have the cloud for data storage and data processing, which is large online servers. But fog is the same kind of cloud, but now it's on the ground and it's all around you. The idea here is that you're bringing what's in the cloud down to where the people are. Now, there are several motivations for this. Number one is when you put things out there on the edge, or when you bring the cloud down to where the people are, you can do things much faster. You have low latency of response. And obviously, if you have poor connectivity, this is a good way of dealing with it because you don't necessarily have to connect to get the information or to do the processing. There can be reduced server load at the central location, but probably one of the most important ones for a lot of consumers is privacy. If the identifying or private information never leaves your phone, if it never leaves your watch, if it never leaves your laptop, if it always stays with you, then you don't have the same kind of privacy concerns that might happen when everything's stored in a single central location. Now, I can give you a few examples of edge or fog computing that are particularly useful. One is facial recognition. This can be done on your phone. Once a network is trained well enough, it can be done right there on your device. You may work in a massive multinational corporation, or you may work in a scrappy young startup. But no matter where you work, you have to make decisions about how you're going to make your business work and reach its potential. And data should always be central to those decisions. Now, maybe you have a simple situation. Maybe you already have consistent profits going up and up and up each month. So in that case, just keep doing what you're doing. Do more of same. Because, maybe you've cornered the market on some new wonder widget and you're growing 10x every year. By all means, just keep what you're doing and enjoy your uninterrupted prosperity. But reality is rarely that simple. Customers' attention wanders, competitors arise, the market gets saturated, and economic environments change. So you have to adapt in that case. Also, you need to identify potential profits, things that you could do to add to your business, and potential risks, things that potentially represent a threat to your operations. Now, you can use data to answer these questions, and maybe you've got some simple methods. Maybe you just look at your sales numbers in a database, up, 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 down, up, up. Or maybe you have customer data in CRM software, that's customer relationship management. And CRM software can be very basic, it can be very sophisticated, it depends on what you have. Also, you have social media accounts and you have websites, and you can look at the built-in analytics for each of those. Those can give you individual images into what's going on in your business. But there's a major problem with all of those approaches. Everybody's doing them. Remember, if you're in the business world, you're in a competitive environment and you need a competitive advantage. So it's pretty obvious that you can't simply do the same things that all of your competitors are doing. At best, you would keep even with them, but it won't put you ahead. You need a competitive advantage. And this is where big data comes in. Remember, big data is data that's characterized by its unusual volume, its high velocity, and its astounding variety of formats and sources. What these together mean is that big data has the potential of giving you a competitive advantage in your business's operations. There's a few different things. For instance, you can identify new patterns in your data. You can find relationships. You can find trends that other people can't because you're able to look at it in a more detailed, nuanced, and responsive way. You can use novel data sources. This is a cell. I know some local companies that do amazing work on biological experiments, conducting hundreds of thousands per week, then using microscopes to take photos of the cells, and then using artificial intelligence to process those photos. It's a novel data source. It's extremely high quality data, and it's actually allowing them to get a huge advantage in the pharmaceutical market. Also, the intelligent use of big data through data science, machine learning, and artificial intelligence allows you to adapt dynamically in real time, not just quarterly or monthly or yearly. It allows you to identify new trends and new markets and start engaging with them immediately. You can become an agile organization through the proper use of big data. Now, let me say just a little bit more about each of these. With the new patterns, big data brings in with it a whole new suite of new algorithms, new ways of processing. It's true that a lot of traditional methods like linear regression can be extraordinarily effective with the proper data. But sometimes your questions go beyond that, and you do need the algorithms that come with the big data revolution. You can focus on exceptional cases, and especially because you're going to have a lot of data. Remember, it's big data. You're going to have a lot of data, and you can focus on those edge cases and identify possibly a new niche that's been untapped. You can follow non-linear patterns. Many other methods assume you can draw a straight line or put a flat plane through it. Many of the big data methods allow you to get much more intricate than that, and there's new methods for identifying clusters of potential clients, of maybe a subgroup that has not been completely addressed. By using the methods that come along with the big data, you have the potential of identifying these new patterns. Now, novel sources. Social media posts are a tremendous way of getting unfiltered and unprompted data from your potential audience. You're going to want to look at product reviews, both on big e-commerce sites and also things like bloggers who review things for their own audience. That's going to give you amazing insight. But again, because it's an unusual kind of data, it's video data or it's unstructured text, that means big data. And that means you're going to need that whole tool set that comes along with it to get the information out of that. Or you can actually use satellite imagery. There are many companies, large companies, that use satellite images of their competitors' parking lots to determine how many people are there, how many people are going in and out, and at what time, as a way of understanding who they're up against in their operations. Or sensor data. Again, this is part of the high velocity element of big data, and that can be one of the novel sources you use in getting a competitive advantage. And then the adaptability or the agility. You can quickly spot changing trends by casting a much wider net. Again, using the naturally arising social media data, looking at these immediate trends, you can anticipate changes in things like shipping costs. In an ideal world, this is how your customers are going to feel every single time they connect with you. They'll be in a state of constant delight. Well, that's the goal, and there's a few ways you can go about trying to understand how you can constantly delight your customers. You can look at things like, what did they buy previously? What's their history with your organization? Or maybe what market segment are they in? So you can look at what other people who were similar to them in some ways have done previously. Use that as a stand-in for their own behavior. Or maybe you can do something like, what have they searched for online, even when they weren't exactly in your own e-commerce site? Well, remember, when you put together these profiles and you're trying to identify what a person is likely to buy, you need to be concerned about the accuracy of your predictions. So you need to look at things like sensitivity. If they're likely to respond to an ad and buy something, so if they actually are in your target audience, make sure to show it to them. So when you have a real candidate, make sure it triggers the response and you show them the thing that they want to see and that they want to get. At the same time, you want to balance that out with specificity, and that is only show ads to people who are likely to respond and buy something. You're wasting time and you're wasting money if you are showing ads and doing these engagements with people who have no interest in what you're doing, or heaven forbid, they already bought it. And it shows that you're not staying on top of things. I mean, truthfully, anybody who's done this and had an ad follow them around on the internet, that's a false positive where they think you're a target and you're not. That makes customers feel like they're being stalked by some organization, and truthfully, it's a creepy feeling, so you don't want to do that. You need to be more precise in your targeting and your categorization of potential customers. Fortunately, that's one of the things that big data lets you do. The reason you can do that is because big data gives you more data sources. It's not just the database of they purchased this, they visited the site here. Again, more sources. You get the unstructured data. Maybe you get some sort of information about the other sites they visit, maybe about information that they make public through comments on websites or posts that they share with other people. You get a wide range of more data sources that you can't analyze with standard methods. In addition to that, you simply get more data by casting a wider net, both in terms of who you address and the kind of sources that you use. You have more total data. And when you have more data, you can identify things with greater precision, more accuracy. You can look at the edge cases and still have enough information to make a good decision. Also, you can be more sensitive to changes in a person's interest, the things that they've already bought, the things that they said online, the things that are happening all around them, and you can adapt to those changes in a more agile manner. And then really, when a person is shopping, for instance, and they're on their phone, you want to benefit from the low latency of edge computing. Let their phone do some of the processing. And if it's properly set up, you can use even your big data algorithms and results in that particular situation. Now, there are a few major benefits of using big data in these ways. Number one, your customers are more likely to feel heard because they know that you have seen what they've said about you. They know you're paying attention to what they want. So feeling heard is number one. Then feeling understood. Not only are you monitoring what's going on, it makes sense to you and you're able to respond appropriately. And appropriately is a major qualification there. That gets back to the specificity of the targeting. And then finally, you are also able to help your One of the great paradoxes of big data is that sometimes all of the technological wizardry, all the equipment, all the huge amount of effort that goes into it is put into motion to help with something as theoretically simple as choosing whether to go left or right at the fork in the road. The idea here is that big data is frequently used to create small data, the small amount of information, the direction, the couple of restaurant recommendations that the end user wants. It's really another example of the general principle that all analysis, all data analysis, is an act of simplification. You are taking something very complex, something potentially huge and overwhelming, and reducing it with hopefully still maintaining the general form and feel to something that is more usable and actionable. Now, in terms of applications based on big data, some of the really common ones are things like directions from point A to point B, or maybe something like finding jobs online, or getting health feedback. And by the way, I intentionally use cell phones in all three of these because mobile devices are going to be one of the greatest ways that people interact with big data. You've got the huge server farms on your end. They've got their phone in their hand at the other end. And that's how you're trying to meet with the end user. Now, think about directions, just for example. In terms of big data, what you're doing is you're bringing in things like GPS coordinates for where the person is, where they want to go. You're bringing in map data, so information about the roads, the shape files that show the map. You're bringing in traffic conditions, historical patterns, and real-time estimates. You're getting user preferences. Do they like to be on the freeways? Do they want the scenic route? Do they want to avoid tolls? And you can also bring in data from other travelers to identify potential slowdowns or detours in the road. This is a very complex set of data, and that's why it is big data. It's the variety, it's the volume, and things can be coming in quickly with the velocity. But you're boiling it down to go straight, turn left, turn right here. That is big data being put into the best possible use for an application with consumer orientation. Or take something like a job search, which can be a very time-consuming, stressful, unpleasant experience. But with big data applications, you can take, for instance, a person's physical location, where they work, where they say they want to work. You can match their skills. You might even be able to assess those skills directly. You can look at the endorsements that people give them and match those skills and endorsements to the requirements of the jobs that you have available. And then probably one of the most important things is you can connect that person through a professional network to other people who have similar jobs, maybe even at the same company. It tremendously facilitates the job search process. And again, these are many different kinds of data. That's how big data is used to compress it down to a small number of jobs and recommendations for the end user. And then as a final example, there are health applications where you're doing things like connecting with medical history, usually self-reported, where the person who owns the phone, they put the information into their account, possibly collecting data from their medical provider's records. That's another big obstacle. But you can also get sensor data from their watch and their phone. How much are they moving around? What's their heart rate? How'd they sleep last night? What's the temperature around them? All of that information, again, very dramatically different kinds, can be integrated into the health app. And you can even use that to connect with emergency help. Again, think about something that a person needs all this information to put together so the watch can say, maybe you fell and maybe you need emergency help. That's taking big Big data isn't just a supersized version of small data. It's qualitatively different in a number of ways that actually matter to what you're doing. In the book Principles of Big Data, Preparing, Sharing, and Analyzing Complex Information, Jules Berman outlines 10 ways, maybe you could say they're the top 10, that big data is different from small data, and I want to walk you through those. First, they differ in their goals. For small data, the goal is usually a specific, singular goal. We're trying to accomplish this one task by analyzing the data. On the other hand, with big data, the goals evolve and they can redirect over time. You may have one when you start, but things can take unexpected directions. Second is location. Small data is usually in one place and often in one computer file or one floppy disk. But big data is much larger because it is big, and the data may be spread across multiple servers in multiple locations anywhere on the internet. Third, the data structure and content. Small data is typically structured in a single table, rows and columns in a table, like a spreadsheet. Big data, on the other hand, can be semi-structured or unstructured across many different sources, and it's putting those things together that constitutes one of the major challenges. The fourth difference is data preparation. Small data is usually prepared by the end user for their own goals. So the person who's putting in, they know why it's there and they know what they're trying to accomplish. On the other hand, big data is generally a team sport, and the data can be prepared by many people who may not be the end users or the analysts at all. And so the degree of coordination that is required for big data is extraordinarily more advanced. The fifth difference has to do with longevity. Small data may be kept for only a limited amount of time after the project is finished. Maybe a few months, maybe a few years, but after that, it can go away. It doesn't really matter. Big data, on the other hand, may be stored in perpetuity, and it actually may become part of later projects. So future data might be added to existing data, historical data, and data from other sources can come in. It evolves over time. The sixth difference has to do with measurements. Small data is typically measured in standardized units using one protocol, usually because one person's doing it and it all happens at one point in time. On the other hand, big data can come in many different formats that are measured in many different units and gathered with many different protocols by different people in different times and places. And so there's no assumption of standardization or uniformity, at least in the raw version of the data. The seventh difference has to do with reproducibility. With small data, projects can usually be reproduced if needed. If your data goes bad or if your data goes missing, you can do it over again. In scientific circles, this kind of replicability is actually considered a very good thing. With big data, however, replication, meaning gathering all the data over again, simply may not be possible or feasible. Bad data may have to be identified through some forensic process, and there may be attempts to directly repair things, or you may have to do without it. The eighth difference has to do with the stakes involved. With small data, because the projects are not huge, the risks are generally limited. If the project doesn't work out, if a mistake is made, it's usually not catastrophic. But with big data projects, because there's so much time and effort and people's work invested in it, these risks are enormous. They can cost hundreds of millions of dollars, and lost data or bad data can doom a project, maybe even the organization that's running the project. The ninth difference goes by a peculiar title for those of you who are not in computer science, and that's introspection. This is a term that comes from object-oriented programming languages like C++, Java, Perl, and so on. It has to do with where the data is and identifying the data. In small data, you generally have well-organized and individual data points that are easy to locate, and they often have clear metadata, so you know where they come from, you know what the values mean. With big data, however, you have many different files in potentially many different formats, and it can be difficult to actually locate the data points that you're looking for. And if they are not well documented and it's easy for things to slip through the cracks, it may be difficult to interpret the data and know exactly what each value means. And the 10th difference has to do with analysis. In small data, you can generally analyze all the data in one procedure on Elsewhere in this course, I've introduced you to the 3 V's of big data. Those are volume and velocity and variety. When you put those together, you have big data. But you may be familiar with another 3-part Venn diagram, this time serving as the tripartite definition of data science that involves hacking skills and math and statistics and substantive expertise, and that together constitutes data science. And this model was created in 2013 by Drew Conway. Now, if you want to use shorter names for each of these, you can call them code and quant and context. By the way, most people have an intuitive feel for why coding and quantitative skills are important to data science, but context or domain expertise might need a little bit of explanation. And I like this quote about why context expertise matters. Organizations already have people who know their own data better than mystical data scientists, and this is a key. The internal people already gained experience and ability to model, research, and analyze. Learning Hadoop or any other big data platform or method is easier than learning the company's business. And that's by Svetlana Sikula of Gartner, Inc. And so the idea here is it's easier to take somebody who understands your business and who understands the way things work within that domain and get them the technical skills than it is to do the other thing. Now, the data science Venn diagram also labels the intersections of pairs of circles. So for instance, here at the intersection of coding ability and quantitative ability is machine learning, according to Drew Conway. And then over here at the intersection of quant and context is traditional research. And then finally, over here in code and context, Drew Conway calls it the danger zone. I have different things to say about that. But the important thing to know about this is that data science and big data for many years were taken as practically synonymous. Elsewhere, I introduced you to the three-part definition of data science that revolves on coding and quantitative abilities and context. And while data science has been strongly associated with big data, it's still possible to do data science projects without involving all of the elements of big data. So for example, you can use data science on projects that have volume without velocity or variety. So for instance, a very large and static data set with a consistent format. Genetic data is going to fall into that category. Or maybe something in data mining or predictive analytics. You may be trying to predict a single outcome, like whether a person will click on an ad on a web page. In this case, the data set might have thousands of variables in billions of cases, but all of it's in a consistent format. The size is a challenge, but otherwise it's a relatively, at least in theory, straightforward analysis. You can also have velocity without volume or variety. So think about streaming data that has a consistent structure. That might be looking at the number of hits on web pages or searches for a particular term, like searches for big data or data science in the last decade on Google Trends. You can also get data from a sensor, like temperature readings, that can come in hundreds of times per second. So this is data stream mining, or sometimes called the real-time classification of streaming sensor data. So you have to do data science to be able to process information that's coming in this fast and adding on to it, even if it doesn't ultimately constitute a large volume or it has a very consistent structure. And then finally, there's variety in the data without necessarily having velocity or volume. So think about, for instance, facial recognition in a personal photograph collection. You might say, maybe you have a few thousand photos. That doesn't exactly constitute big data, but because it's photographs, it does have a lot of variety in the data. But an even better example is a data visualization of a complex but static data set. That involves the data science toolset, even though it's distinct from big data because it's characterized only by one of the three V's. And so data science and big data do have a lot of history in common, a lot of practices in common. But you can see from this that you can do data science even when you don't have all of the elements of big data. You're familiar by now with the three V's of big data, the volume and velocity and variety of the data. And you're also familiar with data science, which involves coding and quantitative ability and context. Now, just as I have shown you that you can do data science without needing big data, you can actually do big data without needing the full data science toolkit, and you can still get valuable and actionable insights from those analyses. And so let's take a look at, for instance, when you would use the coding and the quantitative abilities of data science without necessarily needing the context or the domain expertise. The best example in this case is machine learning, or specifically deep learning neural networks. In this case, you can create a black box, which means you don't necessarily know exactly how the algorithm is processing the data, but you can still get very useful categorizations and identifications of cases that fit, cases that don't fit, of anomalies, and you can find how you can best serve your clients, even without having the strict domain expertise that's normally involved with that. On the other hand, there are projects that involve context expertise and quantitative ability without necessarily requiring the ability to code. Now, in Drew Conway's data science Venn diagram, he calls this traditional research. Now, a person with traditional research training, as is common in my own academic field, is probably going to be very, very good at their context. They'll be experts on it, and they're probably sufficiently skilled with quantitative abilities to get their work done. Chances are they're not prepared to deal with the volume, velocity, or variety of big data on their own. So in this case, those who are best skilled at traditional research may not actually be able to engage in a big data project the way it's traditionally defined. And then finally, there's what Drew Conway calls the danger zone. He says that's when you have the context or the content expertise and the ability to code without having quantitative ability. Now, I can think of lots of situations where that's not going to cause problems. For instance, in the big data world, word counts, where you take large amounts of text, either from individual documents like this or from a collection of social media posts, and counting how often the words happen. There's nothing statistically sophisticated about that, but it can be a great way of processing data, getting an overall feel for what's happening in the document, and seeing how things change over time. these word counts involve, again, most tech companies would think that their wildest dreams had all come true if they could bring in $5 billion of revenue. But to lose $5 billion because you didn't adequately protect people's privacy, well, that would be about your worst nightmare. And that's something that Facebook gets to deal with at this exact moment because of a landmark fine for violating the privacy requirements of the European Union's General Data Protection Regulation, or GDPR. Now, the European Union's GDPR, which has been enforced as of May of 2018, makes some important restrictions. It puts limits on data. Not all data that is accessible, data that you can see online or that you can get from people by asking them, can be legally used. For instance, you may ask for people's phone numbers to enable two-factor authentication, but you can only use the phone number for that purpose. You can't use it for audience targeting or segmentation. Also, there's a dramatically changing landscape when it comes to privacy. The laws and regulations are evolving rapidly, and the interpretations of these regulations. So we're seeing how the GDPR gets interpreted and how it plays out. And then there's things like the California Consumer Privacy Act, which will be enforced in 2020, shares many of the same elements as the GDPR. And many states and most countries have their own versions of privacy regulations, which unfortunately don't always mesh. And so it makes working in an international environment, which is what people on the internet do, a little more challenging. Now, if you want to know specifically what kind of information is considered private by these regulations, here's an answer. Demographic data that indicates racial or ethnic origin, political opinions, religious or philosophical beliefs, trade union membership, genetic data, biometric data for the purpose of uniquely identifying a natural person, data concerning health or data concerning a natural person's sex life or sexual orientation, as well as things like web behavior and IP addresses. That's a huge amount of information that once upon a time would have been part of the free-for-all for internet marketing, but now that information is restricted. And this list, by the way, is from Article 9 of the GDPR. Well, what can you do? There are a few major things that are going to help you get started on proper privacy. So, for instance, the GDPR requires explicit affirmative consent to gather personal data. People have to check the box to say yes, and it can't already be checked. It has to be blank, and they have to check it, and they have to give you permission to gather personal data. But in the process, you have to justify the collection. You have to explain how that data is collected, for what purposes, how it's going to be processed. And then really a critical one here is that the customers control the data. The customers can download all of the data that you collect on them. If they think that there's an error, they can correct it and you have to make the revisions. And they can ask you to completely delete all of their information from your records. So these are the sorts of things that might fall under common sense, civil rights or human rights on the internet, but there are things that had to be codified in the GDPR, and they are now part of the legal and regulatory landscape. Now, it does bring up another question. We have a lot of kinds of information that are not allowed, but how close do you have to be to those things? We have what you might call the minimal or the minimalist interpretation. And the idea here is that only variables that directly record personal characteristics are blocked. So you would have to have a variable or a field that says race or ethnicity or religion. And it would have to be an answer to that direct question. And so the minimal version says, well, only if you ask that specific question. The problem is that nearly all variables on everything are correlated with these kinds of personal characteristics. It's not difficult to infer a person's race or religion or education or so many other things by, for instance, the websites they visit. And so it turns out that the minimal approach, which only looks at direct questions, is ineffective protection because all of these protected categories can be inferred through other processes. Then there's what you might call the maximal approach, and that is that all variables that are even correlated with personal characteristics are blocked and can't be used in targeting audiences and marketing. Well, this approach basically removes all of the data. Everything is out. And the problem is that that maximalist approach makes modeling, that is, creating statistical models to provide the services that your company is designed to do, it makes that nearly impossible. And so, again, it's not a workable solution. So obviously, you're going to have to find some kind of balance between those two extremes. It's going to have to depend on, among other things, the field that you're working in, the kind of data that you have available to you, and of course, My friend is a choreographer, and they've got a box full of early work recorded on Super 8, on Betamax, and a whole bunch of other orphan video formats. One of these days, they'll get them transferred to digital, but until then, these videos constitute a sort of data dead zone. There's data there. It's in their hands. They just can't do anything with it. It's actually an example of data governance gone wrong. Data governance is a lot like taking care of your dance videos or maybe your garden. In a garden, there's a lot of work to do to make sure your plants are healthy and happy, and the same holds true for taking care of your data. There are four major elements of data governance. They concern the availability of data, the usability, the integrity of that data, and the security. And I'll talk a little bit about each of these separately. But I just want to mention, these things are hard enough to do when you have only one machine to take care of. I think all of us have had an example of losing a data file, having it be gone for good, or trying to open a file and have it be corrupted. Well, it's exponentially more complicated when you have big data for several reasons. Number one, there's more people, there's more hands in the data. There's more people working who may not be communicating well, and that dramatically increases the risk of working at cross purposes. There are many more machines. Instead of a single laptop, you've got server or collections of servers or who knows what out there in the cloud. And so you have a lot of different hardware and potentially different software involved. And then you have more formats for your data because big data necessarily involves many different kinds of data. Think about the variability. You have a lot of different formats, and you may be working in many different programming languages because they work well for different things. All of these multiply the complexity of data governance and make that project much more important and challenging when working with big data. Let's talk about the availability first. The question is, where is the data? Can you find it? Is it connected to your current systems, or is it sitting on a hard drive somewhere that you don't know where it is? Is the data restricted? Can only certain people get access to it? As important as computer security is, the moment you don't have the password to the data that you need, you're facing an important availability issue. Second is usability. What format is used for storing the data? Is it on a floppy disk back in your backpack? What language is used for processing the data? There's actually a fair amount of work still done in Fortran, but you're going to have to work a little harder to find somebody who is very comfortable working in that. Or is metadata available? Is there something that describes where the data comes from, how it was collected, who the sample was, what the variables mean, and what the values mean? These are all critical questions to make the data usable and interpretable within the context of your project. Then there's integrity. Are the data files free from corruption? Anybody who's had to deal with this for a single file knows how difficult it can be, and you get muck. If it happens to an entire server, you've got an extraordinarily huge problem. Is the code that's used to process and analyze the data, is the code complete, and is it functional? And you have to worry about whether, for instance, the code has updated between now and then, which is why, for instance, it's common practice to include the usable copies of the packages that you used when you're doing the programming. So those update a lot. This way you always have the version that you know worked. And then, are the relations intact? And by that, I mean the connections between the different tables in your data. You have to have a way of referring between them to make a complete data set. Are those still valid? And then finally, there is the issue of security. Are the data and the code safe from hackers? Remember, data is enormously valuable, and it's a target for anybody who's looking to get a little bit of extra stuff for free. Or in a big data project, because there's so many people involved, you have to be sure that the data and the code are safe from accidental changes by unauthorized users. I think about, for instance, just my genealogical data. I log in there, somebody's made a change. They went back to the same wrong thing that got corrected, and you got this big problem. Think about what happens on Wikipedia, the little editing wars. But people sometimes log in, and if they have access, they might make a change without realizing how much impact they're having on other major projects. And then the last one, to get back to our Fortran issue, are they future-proof? Can you store the data? Can you store the code in such a way that you know it will be usable at least a few years from now? Maybe not forever, but at least a few years. So, for instance, if possible, don't store your data in a proprietary format, which requires a license and I have a friend who worked as an archivist for a major fashion designer in New York City. Their job was to go through the disorganized racks and piles of clothes from several decades of runway shows, match them with the videos of the shows, and then label and document and organize everything. It was a monumental task that took over a year, but now the design house has a documented history of their creative work, and in addition, they can actually find what they're looking for. In fashion, as in life, a little bit of structure can go a long way. When it comes to data and structure, there are three major rubrics or categories. There's structured data, semi-structured data, and unstructured. And I'll say a couple words about each of these. Structured data is the kind that you generally think of when you think of data. It's rows and columns organized and labeled. The variables are predefined. The last name goes here, the first name goes here, the zip code goes here. Spreadsheets are a perfect example of structured data, provided that each row is a case and each column is a variable or field. Relational databases are also a perfect example of structured data. Things are well defined. You know where things are, you know how they connect, and it makes analysis very easy. On the other hand, here in the data science world, we get to deal a lot with semi-structured data. Now, this involves variables that are defined, but they're defined on a one-on-one basis and marked with tags. And those tags can vary freely. Good examples of this are HTML, that's a hypertext markup language that creates web pages, or XML, extensible markup language, and JSON, the JavaScript object notation. And all of these are used extensively on the web. And what you see here on the right is some data that I've used in other examples, but saved not as a CSV file, because it's normally in a spreadsheet, but I've saved it as a JSON file. And so you can see within the curly brackets are each case, and then in each line, it defines first what the name of that variable or field is, like state, and then it gives the value for that case, California, and so on. Now, these have consistent names, but they can vary from one document or one case to another. And then finally, there's unstructured data. This is when the variables or the fields are not labeled or identified. Instead, you have a lot of information there that you have to figure out what it is. Free text is an example. If you import the text of a book, or you take photos or videos or audio waves like we have right here, those are extremely common forms of data, but they're not used traditionally a lot in analysis because they're not structured, they're not labeled, they're not processed in a way to make analysis easy. And that gets at a little paradox here. If we take these three versions of data and look at their ease of analysis, structured data is by far the best. It's ready to go. It's all set up. Semi-structured data takes a little bit of work, but you can import a package into your programming language that knows how to parse it, and it adds a few extra steps, but it's not a big deal. Unstructured data, on the other hand, requires sometimes an amazing amount of mental and statistical gymnastics to get the data set for analysis. So from ease, it's structured to semi-structured to unstructured being the hardest. On the other hand, if you want to talk about the quantity of data that is theoretically available out there in the world, well, there's more unstructured data than anything else, especially when you consider all the social media posts, all the books ever written, all the songs ever recorded, all the movies ever made. All of those are unstructured. And there's an enormous wealth there, but it takes some work to get at it. Semi-structured, there's a lot of data that, for instance, is on the internet. Social media data is, in certain respects, semi-structured, and web pages are largely semi-structured, at least in the gross elements. And then structured data, the stuff that's all set up and ready to go, well, it's the easiest to work with, and it's what I turn to first. It is probably the least common in terms of overall quantity of data that's theoretically available. This means that there's a problem, this mismatch between the ease of analysis and the quantity. And that means that basically you have to find a way to take the unstructured data and to put some kind of structure on it. You can do that by either manually labeling the data, like grading papers and giving a score to them, or taking a document and saying what it's about. You can do it yourself. You can hire other people to do it. You can wait for users to label their own photographs. Or what's shown itself to be really useful these days is to use machine learning to create and apply the labels. This has been one of the great benefits of deep learning neural networks. They take messy unstructured data like audio, video, MRI scans, and so on, and through a sophisticated procedure, they are able to label the data and do so at scale, which is one of the great benefits. So It's one way of dealing with this mismatch between the ease of analysis and the quantity of the data available. But what it lets you know overall is that there are these different kinds of data, that the structured is easy and ready to go. Semi-structured is pretty common. Unstructured is an enormous untapped resource, and that's one of the major challenges of big data, and by extension, data science and machine learning and artificial intelligence, to take that unstructured data and get the value and the meaning out of it. Jazz music is inseparably connected with improvisation. With a small combo, it's possible to have just the outlines of the tune and then create the whole thing on the go. When it works well, it can be an extraordinary experience. But once you have more than a few musicians, say the 15 to 20 that are in a big band, you can still have improvised solos, but everything else usually has to be composed in advance to work well, to coordinate, and make a wonderful experience. There's an analogy between improvisation and composition in music and in data. In jazz, the improvisation, the coming up in the stream of the moment versus the composition where the work has to be done ahead of time and you got to put a bow on it before you move on. That's a lot like in data, what is called stream processing, where you're processing the data as it comes in live in real time, versus batch processing, where you take data that's been wrapped up and put a bow on it. It's in a data set, it's set, and you run with it. Now, let's take a quick look at this. Batch processing is data at rest, meaning it's static, it's stationary. Now, I'm not trying to talk it down. This is the kind of data that I work with. It's data that's in a data set, and it's what it is. And you can analyze that data in as much detail as you desire. You have time to go back and forth with it. You can look for patterns. You can find groups. You can make predictions based on rather sophisticated and time-consuming models. All of those are possibilities with standard batch data. Create the data, put it together, say it's done, then do the analysis and do your work. Compare that to stream. Instead of having your baskets of apples, and they're now on a conveyor belt, the data is constantly arriving. You may not even keep the old data. Maybe you just have a window of data that you're saving because maybe you're just looking for changes over a short period of time, or you're looking for significant anomalies that might, for instance, trigger a problem with the system, a potential breakdown with the machine, an attempt at fraud, as something that triggers the next actions that result from your analysis. Now, I do want to make one important distinction. Everybody likes to have an organization that operates efficiently and responds well to changing situations. That's one reason why agile development and management are so popular. And so there may be an automatic preference for a data approach that seems speedy and responsive and maybe agile too. But the thing to remember is that stream processing isn't better. It's not a new and improved version of batch processing. It's a different process. Streaming data and streaming analysis often relies on a different infrastructure. You use different kinds of storage systems. You have different kinds of databases. You have different ways of incorporating the data. It often uses different methods. You can't do an elaborate neural network on streaming data. You often have to simplify the model depending on the kind of data and the volume that you have coming in. And most significantly, stream processing has different goals than batch processing. Again, stream processing is designed to look for very quick trends or immediate anomalies, something that requires immediate action, something where the business simply can't survive without that moment-to-moment responsiveness. Batch processing is designed to allow you to look at things in more depth, and that is the traditional method of working with data. And so my point here is simply to tell you that these two approaches exist. They're two different paths. And depending on the purposes of your organization, you will want one or the other. But generally, it's important to remember that they serve different goals, use different methods. And so it's a decision that you need to consult with the people on your data science team. And when you're doing your big data projects, you need to think about it carefully and see how well that matches up with the goals of your organization. One of my great accomplishments is that a few years ago, my family and I traveled around the world using just carry-on bags. Now, we had to be very, very selective about what we took with us, and occasionally we had to buy stuff when we were there. But a few weeks ago, we went on a short trip, and our car ended up looking more like this. It's not that we don't know how to pack anymore, it's just that our trip required a lot more things. That's the same thing about data. Big data, of course, is big. Often, because of the extraordinary volume of the data, you can't fit it all on a single file or a single drive or a single computer, nor can you process it that way. Instead, you frequently have to turn to distributed computing and processing. Now, several years ago, Apache Hadoop was the first major solution to distributed storage, and it really ushered in the big data age. And for that reason, Hadoop became synonymous with big data. Major conferences were named the Hadoop Conference, and people used it as a way of symbolizing big data. Now, what it did is it allowed you to spread the same data set across many, many different computers. It could take care of the redundancy. It could take care of the fault problems. It could do an amazing number of things. But it was built for local storage, and it wasn't built for processing. And so Hadoop, while it initiated the big data age through the distributed storage and certain kinds of distributed processing, it really was a foundation and not the ultimate solution. So, for instance, right now we're in the age of cloud. If you've been in the tech world or even just watching for more than, say, 6 months, then one thing is clear. It's a roller coaster. It's got constant ups and downs and twists and turns. It's never the same, and as a result, it's also always exciting. I've mentioned elsewhere how the changes in the data world, as anywhere, build on one another, like climbing stairs. Data science led to big data, which led to machine learning, which led to artificial intelligence as we now know it, and so on, up and up, step by step. And one implication of that is that anything I could tell you about specific technologies or practices, like Docker containers or Kubernetes, will almost inevitably be obsolete within just a few years. But this is not a cry of hopelessness. Rather, it's a call to action. The idea here is that there will always be new technology. There will be new hardware and new software that can be used for collecting data, processing data, storing and analyzing data. And it becomes really a critical task to not just know what those new, better, wonderful, shinier things are, but to integrate those innovations with your current systems. And that's where some of the current developments, like multi-cloud, where you use multiple cloud providers simultaneously for storing data and for processing data, and container systems, which make it so easy to develop an app on your big data system and run it almost anywhere, those allow you to integrate, and they allow you to include these new technologies, as well as some of your legacy systems or the things that have proven to be very effective. Similarly, there will always be new methods. For instance, there have been extraordinary developments, really groundbreaking work with deep learning neural networks. They've accomplished things that I personally never would have thought were possible. And so have other new developments in the data science world in general. But remember, new methods will always come. As amazing as deep learning is, it's not going to be the answer always for everything, at least not in its current variation. And don't forget that old methods, things as simple as spreadsheets and simple as bash programming in the terminal, still have value and still allow you to get insight out of your data, even when you have all of these amazing new technologies. The idea is this: you need to be flexible. You need to remember that you don't have this one system that's always going to work for everything, but you need to be willing to try new things out, and you need to be willing to try a different approach. Then you need to be able to integrate. Don't throw out everything and start over again because something looks newer and better. There's always a cost with making changes, and doing things gradually and testing as you go is critical. But integrating, which has become easier to do with some of the new developments, where you include these new technologies, these new methods, along with the ones that you already have established and the ones you know how to work, that's going to be key to continual success as opposed to the risk of crashing and burning completely. But no matter what you do, remember to focus on your goals. We don't do data science. We don't work with big data just for the sake of it. It's there to help us get useful insights, to actually know what to do to solve a particular problem. And the new hardware, the new software, the new methods are nothing more than tools to help you reach those goals. So focus on your goals and let those be the guiding factor in your decisions about whether to include new technologies, how to integrate them into your workflow, and how you can get value out of them. Now, one really important thing, in case it's not completely obvious, is that because of the changing environment, there is a critical need for continual training and support, not just for the tech people, but for everybody in your organization to better understand how they can use data and big data to inform their own decisions and how they can get the value out of it. And for instance, managers need to know what kinds of decisions can be answered, what kind of support they need to give to the people who will be doing the technical work on a daily basis, and how salespeople can integrate that into the work that they're doing. The training and support is necessary anytime you have a competitive Salmon can be farmed or they can be caught wild. But either way, it takes a fair amount of work before they're turned into this. Everybody knows that food prep is an important, although time-consuming and frequently tedious, part of cooking. There's a similar principle in any big data project. The rule of thumb is that about 80% of the time on a big data project is spent preparing the data, and that's been my own experience. Now, there are several reasons why this may be the case. It includes things like, how is the data entered? If you're using wild-caught data, meaning data that you found out there in the world and that maybe was entered with free text, you have to look at things like place names. Here are 4 different ways of indicating California. You can write it out, you can use various abbreviations, and the inclusion of a period, at least by default, marks it as a separate answer than the one without a period. Or when people are putting in dates, here are 4 different ways of writing the same dates. Now, humans looking at these know that they refer to the same thing, but a computer will read them by default as different things, and you have to do a little bit of cleanup work to make sure that the dates are all read the same way and formatted the same way. Or phone numbers. Again, the same phone number in 4 different ways. You know, for instance, that if you have these in a spreadsheet, they're going to sort separately, but you can reformat them so it knows that they're all phone numbers, it does them appropriately, and it's this kind of cleanup work that becomes an important part of getting things ready for your big data project. Then there are other issues like unit of measurement. If you ask for somebody's weight and they put 150 or 68 or 10.7, well, 150 is pounds, 68 kilograms is the same weight, and 10.7 stone if you're dealing with somebody from the United Kingdom. That also is 150 pounds. So several different ways of measuring these. And we all know about examples where, for instance, NASA has not adequately converted from one unit to another and space probes have crashed as a result of that. Then there are errors. If a person puts in 2.7 children, that's not possible. You can't have fractional children. You can have an average that's fractional. Or 270 children, too many. Or negative 27. You can't have a negative number on a counted value like this. And then, of course, missing data. In some data sets, an 8 might indicate a missing value, a negative 999 might indicate a missing, or a period, or simply an empty space. And there are different kinds of missingness. You can have not a number, not available, missing completely at random. All of them mean different things. And when you're preparing your data, you have to go through these and be thorough in getting them all in the same format with the same meaning and interpretation all the way through. And of course, that's to say nothing of the amount of processing required for dealing with unstructured data like cell phone videos. And it gets to an interesting question. Where's the return on investment and where's the balance point? Should you clean wild data or should you gather new data that is in the structure and with the encodings that you want? So for instance, here's a microscope image of cancer cells. And if you're dealing with things like health records, the project can be a nightmare, which is why companies like, for instance, Recursion Pharmaceuticals, who do drug development where they try to find applications of existing drugs to orphan diseases, they figured out that it was cheaper, faster, and easier to develop their own technology to gather and analyze data from 500,000 experiments per week with a goal of soon hitting 1 million per week, they did the math and realized that gathering their own data with their own proprietary methods so they could then feed it into their algorithms for analyzing the data would be the best way to reach their goals, as opposed to trying to clean the wild-caught data. And so it becomes a trade-off. And depending on your exact circumstances, you might be able to use the wild data. You may need to gather new, custom, bespoke data. In Alice's Adventures in Wonderland by Lewis Carroll, Alice, here on the left, gets some life advice from the Duchess here on the right. This is what the Duchess tells Alice. Never imagine yourself not to be otherwise than what it might appear to others that what you were or might have been was not otherwise than what you had been would have appeared to them to be otherwise. Now, remember, Lewis Carroll was an accomplished mathematician and logician. This is a logically consistent and meaningful statement, but it's nearly impossible to follow. Fortunately, the Duchess provided a shorter version as well, where she simply says, be what you would seem to be, or even shorter, be authentic. Now, anytime you work with data, you're attempting to simplify the data so that it makes sense and you can get some insight. It is always a matter of simplification. That's the purpose of data analysis in big data projects, and that's one of the major things you can do with data visualization. Now, in terms of how you frame things, it's important to remember who is making and implementing the final decision. Is it a machine learning algorithm? So decisions by machines, you don't need to explain them. You don't necessarily need to visualize them. It's going to know based on its calculations whether to recommend a particular product to somebody or not. But for decisions that are made by humans, that's where they're generally looking for the principles or the abstract concepts that come out of the analysis that they can use to guide their own decisions. And in that case, visualization is going to be critical to get the value out of your big data project. Remember, humans are visual animals, and you get much higher bandwidth with graphics. A picture is, after all, worth 1,000 words. And so let me make a few recommendations for your graphics in a big data project or anywhere. Number one, make the graphic as simple as possible. Now, what I mean to say by that, as simple as fits the data. Make it no simpler. You want to make it as clear as possible to focus on the data and not get distracted by other things going on in the graphics. Second, it's a really good idea to provide a method to give detail as needed. Let them click on things, drill down, get some of the source data, get additional context. That gives richness to a graphic, especially one that is initially rather simple. And then to state the obvious, provide labels for your axes. What's on the X, what's on the Y, what are the different groups, and give the sources for your data so the meaning of it is complete. And then there are a few things to be cautious about. First, be cautious of 3D graphics. Now, there's one kind, which is the false third dimension, like you see right here, where you have bars that have depth. There's basically no reason to ever do that. The other one is a 3D graphic, like a 3D scatter plot. It's really cool as long as it's moving, but as soon as it stops, it's very difficult to read. And I personally never use them, and I recommend that people avoid them unless there's some really compelling reason to include it. Another one that's a little contentious is the issue of interactivity, not just with VR goggles, but really putting radio buttons and sliders on your graphics. The risk is this. People will get distracted by the interactivity, and they'll just start playing with it, spinning around your graph and clicking on things to see what happens. At that point, the interface has taken attention away from the data itself, and that's a delicate balance, something you need to think about carefully. Closely related to that is the use of novel graphs like this one. They're cool, they're pretty, they attract attention, they are often very hard to read, and hard to read well enough to know what to do about it. Now, doesn't mean don't use them, it means be very careful and thoughtful when you think about using a novel kind of graph. Truthfully, in terms of the best ROI or return on investment or the best value, the most information from a graphic, it's going to be really simple ones. Bar charts, histograms, line charts, and scatter plots will probably get you 90-95% of the value you need from data visualization, even on a large, big Back several generations in my family tree, I have some ancestors who were miners. They would go down to work in the mines early Monday morning and wouldn't come back up until Saturday night. It was back-breaking and lung-blackening work that I'm grateful I would never have to do. But to be perfectly clear, that's not what we're talking about when we're talking about data mining. Rather, data mining is the practice of working with large data sets to find potentially valuable insight. Think of it this way. Computer algorithms, especially deep learning neural networks, are able to go through millions of images and automatically identify all of the pictures with cats in them and show you where the cats are. They draw the frame around them. Data mining is a little like that, but instead of finding cats, maybe you're trying to find new customers or new treatments for diseases or students with exceptional potential. Really, anything that's important to you using the same general concept. The idea is pretty simple. You get a lot of data in your computer, millions of cases and maybe thousands of variables, and you have the algorithm start looking for patterns of some kind in the data. Now, there is one major risk in doing all this, and that is what I personally call baseball stats. That's not to be confused with the real data of baseball, but you get things like this. The batter is a career 3 for 3 against left-handed relief pitchers on interleague play before the 8th inning on away games when the team is leading by at least 4 runs after the All-Star break. And you got to wonder how the batter's even been up to bat 3 times. This is capitalizing on chance. These are such small numbers that these are meaningless patterns, even if they give people something to talk about. The major challenge in data mining is to find patterns but not get these kinds of false positives. And in fact, it is false positives that are one of the major risks. That's if somebody rolls a 12 with 2 dice, that might mean something if it's a good outcome. And if they do it again, you might suddenly think they know how to roll a 12. Well, that's not really the case, because what you're failing to do is to adequately account for the role of chance. Lots of things can happen at random. A person can flip 10 heads in a row. It doesn't happen very often, but there's a known probability for that. And it's important to always know what is the normal variation, and maybe slightly beyond that, to say this is normal. And when you start looking at many, many possible effects, that becomes critical. And that's one reason anytime you do a data mining project, you especially need to be careful about doing verification. That's the double checking. That's seeing if your pattern holds up in a different data set. That's why it's common in data science to break up your original data set into what's called a training data set and a testing or validation data set to control for these tendencies towards false positives. But if you can do that, there's some great insights you can get out of data mining. For instance, you can find new market segments, groups of people whose interests have not been adequately addressed before. You've got another niche there, something you can do. You can also look for new kinds of product and market match, especially when it turns out that a product can be used in unexpected, novel ways. There's things like market basket analysis, where you can say that anytime a person buys this and this, there's an increased probability they will also buy this. So if you're doing e-commerce, you show them that extra item online, or you give them an incentive to buy it. And then there's a whole separate category of time series mining, where you're looking for events that happen over time, or the closely related sequence mining, where you're not saying when they happen, just that it happened before this and after that. Both of those can be enormously useful in predicting trends with the interactions you have with businesses or customers. Now, if you'd like more information on this, we have another course. I've been teaching in universities for over 20 years, but it took me more than a decade to come to grips with one common element of that job: grading papers. The fact is, reading research papers, giving useful feedback, and assigning grades takes a lot of time, and frequently I could get overwhelmed by the effort, the cognitive energy it took. But if you're working in the online world, then you know that that sort of unstructured text information can come in much, much faster than even student papers. Dealing with that fire hose of feedback is a huge challenge for anyone, and that's the entire point of text analytics in big data. Now, there are a few major challenges that prompt all of this. Number one, text is unstructured data. It's there. It's in sentences and paragraphs and words. It's not broken down into this is a variable, this is a topic. Also, you can have text from multiple sources. You can have comments and reviews online. You can have people forwarding tweets and adding posts. And then you might also want to look at the connections between the people and the text that they put together. That can give you some very rich context on what's going on there. So this is hard to do, but there are some major benefits to this. Number one is that you're getting unprompted data. In the research world, if you can only get data when you ask people the question and they know you're asking, you don't necessarily get to know their unfiltered thoughts. And you do get to know that through social media. You also frequently get the metadata. So when a person posts a tweet, they don't just have the text. You get to know where they were, the time of day. You can look up the weather. You can see how many connections they were, how many times they got liked. You got a lot of information there that's potentially available to help you interpret that text. And really, more than anything, when you start dealing with unstructured text, you have a massive quantity of data available to you. Now, there are a few general steps in text analytics. Number one is to parse the text. It's like taking the newspaper and cutting it up into little bits and pieces. You split it up into words. Maybe you remove the punctuation. You put it all together into this list. And then at the most basic level, you count the words and the phrases, their absolute frequency or their relative frequency. And then using that data, you are then able to do things like model the topics. How often does this set of words having to do with this particular topic come up? Are people generally positive or negative about that? Although that ties into sentiment analysis, which we'll talk about elsewhere. But you can look at some great examples of this. For instance, back in the early 60s, Frederick Mosteller and David Wallace pioneered the statistical analysis of text in a project to determine the authorship of several disputed Federalist papers from the 1700s, which led to the founding of the United States. They did this by looking at how common particular words and punctuation were in the papers that they knew who wrote them, and used it to compare it with the other ones. Now, more recently, Tahir Hemphill and the Rap Research Lab created the Hip Hop Word Count, one of my very favorite free text projects, and that allowed them to explore the ways that concepts, as revealed in hip hop music, evolve both across time and across The best thing anybody's ever said about the videos I make is that they were better than bacon. Now, I took that as a huge compliment. And if you're in business or interacting with people in some way, then you know it's usually a good idea to know how things are going over with people. Elsewhere, I've talked about text analytics, and you can think of sentiment analysis as a special kind of text analytics. You have three major goals. First, what are people saying about you? Second, and this is the sentiment part, how do they feel about what you do? And then that leads to a natural third one within your organizational setting is, what can you do about it? Taking that feedback, the content, the affective valence of the content, and then what can you do about it? Now, the easiest way to do sentiment analysis is to use a package for a language like Python or R that has a well-tested dictionary of affective or emotional terms. And so you feed the content into it, and it will actually create a score for the sentiment value, positive, negative, ambivalent, and then you can use that as the data that guides you in your decisions. Now, there are a few extra complications. If you want to, you can do something called intent analysis. This is related. It says, does the message relate to an opinion, marketing, a suggestion, a query, a complaint, or something else? But does it indicate something that they are planning or intending to do? And there's also contextual semantic search, or CSS. And are they talking about the product's quality? Are they talking about its price? Are they talking about customer service? And so on. In each case, what you're doing is you're taking the sentiment and you're attaching it to a particular object to let you know how you need to respond. Now, there are a few things that can make sentiment analysis, like text analytics, pretty tricky. Number one are differences in vocabulary, by time, by region, by first language. The use of slang and double entendres, any one of these makes the task more difficult. Not impossible, just more difficult. There are also variations in spelling and grammar. As I talked about in text analytics, you need to account for these variations in spelling and realize that those are fundamentally the same thing that they're talking about. Then there's the use of irony and sarcasm, where the written literal meaning is often opposite of the intended meaning, and you have to have a way of compensating for that, especially if irony and sarcasm account for a substantial portion of your data. And then there's the issue of non-text data in sentiment analysis. You may go, well, what does that mean? The most obvious one is emojis as evaluative data. So each of these emojis, which come up in reviews, come up on social media posts, they tell you something about how the person feels about what you've said or about the product or the service you offer. Now, the nice thing is each of these emojis has code beneath it that lets you know what it is, and you can then treat that largely the same way you treat text. But then you can start looking at things like memes that people post. If it's about your product, your service, your company, then those become an important part of evaluating the affective or emotional inclinations toward you as well. And then beyond that, you can actually use sentiment analysis as a form of added value in other projects. Just a few days ago, the Sentimate chess algorithm, which was developed by researchers at University College in London, they found a way to do sentiment analysis to train AI that plays chess. Specifically, they looked at critics' evaluations of recorded chess games. And they're looking for evaluative terms, things like brilliant or ingenious or foolish or stupid. Then they use those critiques of chess play to reinforce the chess playing algorithm. So that sentiment becomes a guiding principle in setting up their I'm a psychology professor, and if there's one thing I can tell you for sure, it's that people are hard to understand. And that's why, after more than 2 decades, I'm still working at it. But you don't have to understand people completely and be able to predict their behavior perfectly in order to accomplish something worthwhile. Really, all you need is more insight and better predictions than you might have had otherwise. And this is where we come into the field of predictive analytics. But first, I want to mention that there are 2 different meanings to the word predict in predictive analytics. The first is to use the standard one, that is to look into the future, say what's going to happen at some later point in time. So we're talking about future events. But also, in predictive analytics, a very common use is to talk about alternative events. So maybe not in the future, but what would happen if an algorithm were to classify photos? Could it do it in the same way that a human would? Could the algorithm predict what a person would do in the same situation? And you'll find that some of the algorithms are used more frequently for the looking into the future, whereas others are looked more often for the alternative, what would a human do in this situation? Now, in terms of predicting values, you might try to predict future quantitative or categorical outcomes. So you might want to predict something like the value of future purchases by a particular client, or the likelihood of remission of a disease in a patient. In these cases, regression or linear regression is a flexible and easy to interpret approach. Here you see a picture of a scatter plot. We've got an x-axis on the bottom, a y-axis up the side, and dots to indicate the scores. And that line is the regression line that allows us to predict values. Now, regression is a tremendously flexible approach. There's about 1 million variations on it that can adapt to the different needs of your data. You might get an equation that looks a little bit like this that says we're trying to predict the y outcome for individual I, and then we have an intercept, and then we have several variables given by x, and we multiply all of them by their various coefficients, and that gives us a predicted score. Now, more often what's going to happen is you would actually run the computer and it would simply tell you what the predicted scores were for each person, but this is the kind of the calculating that's going into it. You may also be interested in classifying cases. And for instance, you're looking at photos and you want to say, what group would a human rater put the case in? So if a person were looking at this photo, what would they say is in it? And there are different methods there. There's k-means clustering, where k is the number of groups that you want to create. There's also k-nearest neighbors, where you put a photo into a category based on what the other photos that are similar to it are in. There are decision trees, and in their plural, the random forests. And there are neural networks in many variations, and especially deep learning neural networks. And all of those allow you to estimate how a human would classify this if they had enough time to go through all of the data, or at times to predict what would happen in the future. But again, remember, people are complex, and while you may not be able to predict or classify things with perfect accuracy, that's usually not the goal. I mean, the rate of agreement between 2 trained human raters is never 100%. Just get 2 doctors to evaluate the same patient. So what you're looking for is incremental improvement, step by step, or the ability to get a better picture and a better idea than you had before, and to do something useful with that insight. That is the goal. That's the reason for being of predictive analytics in the big data world. Sometimes when you're working with big data, you get to play the part of the detective, putting together the clues and drawing the connections between them. Anomaly detection is one place where this practice is absolutely critical. There are a few places where anomaly detection can be really important. One is process failure. You're trying to see if a machine is likely to break down soon, or if a software system is going to fail under a particular load. You might be looking for new areas of potential value, say, for instance, markets that you might have missed, or new product areas, or particular clients that you can use them to identify outliers that have not been adequately addressed previously, like gold in the rough here. And one really important area of anomaly detection is fraud detection, or the ability to stop crimes before they get carried out. Now, in all of these cases, you have a few general approaches. Number one, you can look for cases that don't fit the usual patterns. You can look for outliers that are curious and say, what's going on here? And then get some further investigation to try to understand what gave rise to that anomalous observation. Or, in certain cases, you can simply look for ones that fit known patterns of fraud. When I try to sell things online and a person wants to send me a cashier's check and they want me to mail it out of town, I know it's a fraud. I don't have to do anything else. And both approaches, looking for curious anomalies and cases that fit known fraud, can be very useful for anomaly detection and fraud detection. In terms of the actual algorithms, you have the standard list of choices. You can do things like regression, classification trees, and decision trees. You can use neural networks. Any of these would work for identifying both outliers and cases that fit known patterns of fraud. The kind of data that you're going to be including might include things like the purchase characteristics. What was purchased, for how much, when, where, through what means, and so on. Credit card purchases of gift cards are always suspect, and they're going to set off alarms no matter where. Then there are personal measures, so things like biometrics, scanning your fingerprint or your face, the latency in typing your password or your username, height as estimated by the angle that you hold your cell phone, the signature squiggle that you use when writing your name online, or even just finding the mouse on your computer. All of these can be recorded, and all of these can be used as data to identify the authenticity of the person who's intending to make the purchase. And then, of course, there are general trends. There are new scams going around all the time, and they might be more common in one area or another. Have scammers found a way around old technology? All of these can be used as the data points in identifying whether a particular proposed transaction is fraudulent or legitimate. And this may be the end of this course, but it's just a beginning for you. And so it's time to start making plans on how you're going to produce your own big data revolution. Remember, this course is a map. I've simply been showing you the outlines of big data, the ways that it's used in so many different fields and so many different domains. It's from here that you can plan what you want to do next. Now, I can make a few general recommendations. You're going to get a lot further with big data if you know how to do some computer programming. Python is a very common choice, and R, a statistical programming language, is also a powerful option. It's good to get started with open data, because if you want to have a lot of data and diverse data all at once, going to sources like data.gov can get you started with the sets you need to start finding insight. And then learning more about both machine learning and artificial intelligence. And fortunately, we have a wide range of courses available for you right here to get you started on these more sophisticated topics that can give you potentially greater insight into your own data. Also, because big data works within a context, it's good to know more about business strategy and specifically about data-driven decision-making. And you want to know how these things work and how big data can be applied in your own context, be it enterprise and banking, be it medicine, be it nonprofit healthcare, and even in small businesses. It's also a good idea to get connected with people in big data, in data science, machine learning, and artificial intelligence to get inspired and to get support in what you're learning. You can try events like the Strata Data Conferences, or ODSC, which is for Open Data Science Conference. There are others like the Marketing Analytics and Data Science Conference. That's a small professional conference. And then depending on where you live, you'll have local events. Like I'm in Utah, and each year we have the Silicon Slopes Tech Summit. You'll be able to find a range of opportunities, no matter where you are, either in person or even online, to help get you connected with other people in the big data world, to support you in your learning, and to give you ideas on what you can discover and what you can accomplish with big data. But remember that big data, like all data, is fundamentally about people. The reason you work with big data is so you can better understand the people in the world around you, and also so you can turn that understanding into something of value for the people you work with, be it at a large enterprise scale or at a very small bakery scale. Thanks so much for joining me, and best of luck in your own big data work.